All right, I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day. I just ask you to just bless this help session, Lord. In your name I pray. Amen. So, if I start writing over here or something, I would ask one of you to start working the camera. But until then, I think I should be fine. Do you guys have any questions? Tell you what, I will take your questions in a couple minutes. Let me just take a few minutes to talk about the bit I missed today at the very end of class, just to make sure. So we got to the last page in the lecture 3 here. So I just want to talk through these things. What? Oh, sorry, I'm not in lecture 3, am I? All right, here we go. All right, so I think we did example 2.3.7 in class pretty carefully. We showed Z4 is not isomorphic to U8 by seeing they're both groups of order 4, but we had three elements of order 2 versus just one element of order 2, right? And U8 has no elements of order 4, right? So these are not isomorphic. But then I argued that this set 1i minus 1 minus I is isomorphic to Z4. And I mentioned that this is in fact the fourth roots of unity. Let me just take a minute or two here and say more about that. So, definition, nth roots of unity. So here we go. 1 to the 1 over n is typically the notation for this. And what that is z in the complex numbers such that z to the power n is equal to 1. Now you can prove that this is in fact the set 1 omega sub n squared, omega sub n cubed, omega sub n to the n minus 1, where omega sub n is equal to e to the 2 pi I over n. This is the so-called principal nth root of unity. Now what that means, since I know you guys aren't all familiar with this, but that's cosine of 2 pi over n plus I times the sine of 2 pi over n. All right. So more generally, we're using this identity. E to the I theta is cosine theta plus I sine theta. This is something you should know and you can use in here. It's especially relevant to complex examples. Okay. Now, you can prove that those n elements right there are distinct. I spent about 20 minutes doing this carefully in complex analysis Wednesday. You probably could give a shorter argument. I could foolishly attempt it now. Let's see how it goes. So, no, let me not do that. That's not the point here. Let me show you why those are solutions, all right? So if we take omega sub n to the k power, that would be e to the 2 pi I over n raised to the k power. Now the properties of the exponential say that you can multiply the exponent times the argument here. And, oh man, okay, fine. It's fine. It's just not what I was. I had my mind on something else, and I wrote I wrote this, but I was thinking something else. What happens when we take k equals to n is my question for you. We get what? Omega sub n to the n power is what? E to the 2 pi I n over n, which is e to the 2 pi I. What's that? That's cosine of 2 pi plus I sine 2 pi, which is 1, because sine of 2 pi is 0, but cosine of 2 pi is 1. So certainly the nth, so that means that omega itself, right? Omega sub n itself is a solution. If we take it to the nth power, we get back 1, right? It's an nth root of unity. And a very similar calculation, if we do omega sub n, the kth power of that, if we raise that to the nth power, what's that give us? Well, that gives us omega sub n to the kn, but we can just as well write that omega sub n to the n to the k, which is 1 to the k, which is still 1. So basically, if omega sub n raised to the nth power is 1, then certainly omega sub n to the kth power raised to the nth power is also 1. So certainly everything that I've written in the list of the alleged nth roots of unity are solutions to z to the n minus 1 equal to 0, or z to the n equal to 1 if you prefer. Can you guys tell me why there can't be more than nth roots of unity? So that goes back to polynomial algebra. If we look at this, this is the same as z to the n minus 1 equals to 0, right? So if we look at the polynomial f of z equals z to the n minus 1, this is an nth order polynomial. So if there were more than n complex roots of unity, that would say that you could factor this into more than n linear factors, which would be absurd. Because when you multiplied those factors out, you get a leading term, which is more than z to the n. Right? But that's not up for grabs. So we can have at most n roots of unity, and you can prove carefully that all of these things are in fact distinct. All right? I'm a little apprehensive to try. There's a sentence in the notes which purports to prove it. Do you guys want to write it on the board and see if it makes sense to us? It made sense to me earlier today. When I read it in class, I was like, do I understand this? Ah! Bad things happened to me earlier this week in complex on this issue, so that's why I'm a little bit apprehensive about it. Yeah. Come on, where'd that go? Did I tear out my notes? What's going on here? I don't know where I put I must have taken them out. So here's the alleged proof that they're distinct. It's really just a sentence in these notes, if I remember right. That is very debatable. Come on, where'd you go? I say, so my argument was omega sub n to the k power is explicitly cosine of 2 pi k over n plus I times the sine of 2 pi k over n. So why, can you guys, maybe you guys can just tell me, why cannot that, why is it impossible so that yeah, see, I don't know, I don't, so I say it's impossible for that to be equal to 1 if k is less than n. Does that make sense to you guys? I think that makes sense. If k is less than n, then we're looking at cosine taking values that don't quite reach 2 pi and are between 0 and 2 pi. The only way cosine can be 1 is when it reaches 2 pi or it's at 0, right? So I guess it is clear that that's not equal to, I think that's actually a reasonable claim That's not equal to 1 for k less than n. 0 not included, k less than n. But that's great. That shows that, I mean, but that doesn't completely show that these are distinct, does it? If we want to be picky, what does that show? That shows that these are not 1, right? So that's fantastic. That's not a wrong thing that I said in the notes, but I don't think it's immediately obvious that that proves that there are n things there, because how do you know? How do you know that there's not a repeat in this list? Okay, let's suppose that there was a repeat and see where it takes us. What would it mean to have a repeat in this list? It would mean that omega sub n to the j is equal to omega sub n to the, I guess I better not use k, I better use some other letter. What do you guys want me to use? Q? Okay, I'll take it. Sure. And without loss of generality, let's suppose that j is less than q, right? So those are between what? Between 1 and n minus 1. It could be equalities possible on the edges, right? Somewhere in there. Suppose you have the equality. What would that mean? That would then mean that omega sub n to the, let's see here, let's play my cards right, q minus j, right, is equal to what? So basically take this equation and multiply it on both sides by qn to the power qn to the minus j. So we get 1 on one side, we get qn to the q minus j on the other side, and that equals to what? 1. And what's the problem with that? Is that less than n? If we subtract n from this, we get q minus j is less than what? N minus j minus 1, which is what? Which is less than n, isn't it? It's less than n minus 1, is it not? I think you can say it's less than n, right? The point is that gives us a power less than n, which raises the principal nth root of unity to 1, which we just argued up here was impossible. So that's why showing that the nth root of unity raised to a power is impossible to get 1, from 0 to n, that suffices to prove, in fact, that this list is distinct. I'm not sure if that proof is better or worse than the one I gave in complex this week. I don't know. It's better? Okay, good. All right, enough about this. We should look at the roots of unity for a few small n, and then I'll take all your questions, okay? So let's start out small. What's 1 to the 1/2? This is equal to 1 and minus 1. The reason is simply that e to the 2 pi I over 2 is e to the pi I, which is minus 1. Because cosine of pi is minus 1 and sine of pi is 0. So e to the pi I is minus 1. So the second roots of unity are just the numbers 1 and minus 1. Those form a group of complex numbers of order 2. If you look at the third roots of unity, you got yourself a 1 e to the 2 pi I over 3, e to the 4 pi I over 3. I like to look at this graphically. So you've got the number 1, you've got over here your omega sub 3, and then down here you've got your omega sub 3 squared. And if I did it right, these are on a unit circle, but that's debatable. So those are the third roots of unity. And they form a group, which is isomorphic to Z3, in fact. The fourth roots of unity, that's a little bit easier. Like I told you, it's 1i minus 1 minus I. And that's because omega sub 4 is e to the 2 pi I over 4, which is e to the pi I over 2, which is what? Cosine of pi over 2 plus I sine pi over 2, which is just I again. So the imaginary number I is the principal fourth root of unity, and powers of I generate the powers of I generate the fourth roots of unity, which is plus or minus 1 plus or minus I, and this is a group of order 4, which I pointed out is isomorphic to Z4. You can draw a picture here. So I'll just ask you one question, and I'll stop drawing these things. You can kind of see where I'm going. You know what the fifth roots of unity are going to look like, right? What are the fifth roots of unity? The picture for the fifth roots of unity, what's that look like? I mean, 1 is in there, right? 1 is always a root of unity, so that's always anchoring this kind of picture. What are the fifth roots of unity? So 2 pi divided by 5 is like a fifth of a circle, right? So I got to go like a fifth of a circle around to get to the next one, which is a little bit less than a fourth of a circle. So it's up here somewhere, right? And then another fifth of a circle, which is kind of like, I'm not good at this. It's over here somewhere, maybe. I'm not sure exactly. But I do know this. They have to come in conjugate pairs. Why is that? Why did the roots of unity of odd order have to come in conjugate pairs? Well, actually, why does the root of unity, why do complex roots of unity have to come in conjugate pairs? You go back to what they are. They're zeros of this polynomial, but you could maybe look at this polynomial this way. Notice that it's a real polynomial, and we know zeros to a real polynomial come in complex conjugate pairs. So if you have a complex root of unity, like one that involves an imaginary number, there has to be a partner of it on the other side of the x-axis, which is related, just the complex conjugate. So like, in other words, this omega 3 squared is the complex conjugate of omega sub 3. One other fun fact, and I'll stop talking about it. What do you think the sum of the roots of unity should be? I can start us out with 1/2 1. What's 1 plus minus 1? 0. What about the third ones? What would the sum of those be? Still 0. How about the fourth ones? 0. Fifth? In fact, the sum of the nth roots of unity should be 0. Can you see that? It's just by symmetry. They're arranged symmetrically around the origin, and the origin is their, center of mass if you want to bring physics into it. Let's say it's the centroid, though. Let's keep physics out of it. The geometric center of the roots of unity is the origin. Yeah. Okay, that's all I got to say about the roots of unity. I think that'll be more than enough for us. It's just another example in this course. It's not like the be-all, end-all of what we're doing in here. So with that, I will shut up. Do you guys have questions about homework? Welcome to ask. I should mention, since not everyone was here, that should probably see this. As you're working on the Euclidean algorithm kind of problems, you can check your answer with my little brother Bill's handy dandy Euclidean algorithm calculator. Super awesome. Come on. You can do it. You can do it. Come on, you did it earlier. Now you have it in you. All right, there we go. So like, oh no, the answers to your problem. So you can plug in A here, B here. This will show you the steps of the Euclidean algorithm, and here's what comes as a result of the back substitution down there. And so, I'm sorry, I'm spoiling the answer to part D, but apparently the inverse of 6 mod 1001 is 167, yeah. Which is, if you just start guessing numbers, that's obvious, right? Like 6 times 167 is 1002, right? Obviously, right? No, it's not really obvious, is it? Anyway. Hey, if you're like me and half of the people I've helped this week, if you're making a mistake, odds-on favorite for making a mistake with the Euclidean algorithm. I'm starting to see a pattern. I've seen this with multiple students now. And I am easily fished into it. So if you try to get me to help you, I will just follow you down the garden path. When you're doing Euclidean algorithm, it is important to bring 6 here, not 166. So if you're lost right now and watching this, I wonder if that's the reason why. Just saying. That was not, so the person, I will not call you out by name. I will not name names, but the person who said this to me is not the first person this week who has said these things. And I'd like to say that I didn't make exactly the same mistake they did last time they asked me about it either, but that would probably be a little bit dishonest. Again, I should mention the vector algorithm for doing this is better, and if you want to learn it, you should ask someone who took Dr. Smith's number theory class. They will teach it to you. Or you can ask Dr. Smith directly, what's the vector algorithm for Euclidean algorithm? He'll show you. Although he won't call it the vector algorithm, he'll just call it the correct algorithm. Yes, he'll say, it is the Euclidean algorithm. What's wrong with you people? Yes. Well, he said, I think he would say that the way this is done is not the wise extension, because my brother is actually thinking about doing the back substitution behind the scenes, but I don't know. It's like solving a system of equations. Is it right to multiply by a matrix inverse, or is it right to do back substitution? I don't know. I mean, for a small enough system, back substitution is something everyone understands. So it has that advantage. It's a question of pedagogy, in some sense. If you guys don't have any questions, I'm just going to go home. Oh, okay. You want me to go home and be with my family, you monsters? Which? Yes, go ahead.
Oh, wait, question. Well, I don't have a specific question, but I was wondering if you could do an example or two of multiplying the permutations.
Ah, yeah.
That's my question.
That is
There it is.
That was a very, I do have a link to, I'm sure there are websites you can check your answer on that too. But you can't find one? Well, I'll tell you what, let's do an example. All right, let's get nuts. Find the disjoint cycle factorization of sigma tau, where sigma is 1, 2, 3, 6, 5, 6, 4, 8, 9. And tau is equal to 3, 5, 7. Okay, sure, why not? So let's work it out. Sigma tau. So we've got 1, 2, 3, 6, 5, 6, 4, 8, 9, 3, 5, 7. I'm going to give you guys about 10 seconds to copy that down. This is something I should emphasize. When you're first learning this, you should not hurry. This is important because hurrying wastes your time. You have to be careful and keep track. And don't talk to somebody when you're doing this. Forget about it. Certainly don't go to a football game. That is, don't even think about going to football games. I mean, that's not hard for me. But, so, let's see here. And then you got to start somewhere. So, listen, I write a 1 down, right? So what what we're actually calculating is sigma tau of 1 in some sense, all right? I mean, so how does sigma tau act on 1? This is by definition sigma of tau of 1, right? So what does tau do to 1? This is tau, right? Tau does nothing to 1. 1 is not moved by tau. So this is really just sigma of 1. And then so I feed 1 into here. What does 1 happen? Anything happen with 8, 9 to 1? No. How about here? Is there a 1 in here? No. So in fact, 1 is fixed by all 3 of these cycles. 1 is moved to 2 here, though. So and once you get to here, end of the road, wherever you get to, you write down 2. Then you got to take that 2 and go back to where you started and see what happens next. Does tau do anything to 2? It does not. Then the 2 then moves on to 8, 9. Anything happen? Nope. Does 2 goes to 4, 5, 6, 4. Does 2 go anywhere here? Nope. Then finally 2 gets to 1, 2, 3, 6. Finally something happens. So 2 goes to 3. We're at the end of the road, we write the 3 down. Now we have to go back. And again, start at the rightmost cycle and work our way right to left. So obviously, I would point out, this is a reason that children should be taught to read manga. Right? You should be taught to read things right to left at least some point in your life. If you had read more Japanese cartoons, this would be more natural to you. Oh, and you shouldn't make these kind of digressive comments in the middle of these calculations because you'll forget where you are. So 3. Okay, so 3 goes to 5. All right, 3 goes to 5. Great. Now about 5. Where's 5 go? Notice after I get here, I'm thinking about 5. I don't think about 3 anymore, right? So 3 goes to 5. Is 5 going anywhere? No. 5 goes to 6. All right. I'm not done yet, though, right? Not the end of the line. Now I have to think about what happens when I feed 6 into this one. 6 goes to, loops back to 1. But 1 is here already, which means 3 gets sent to 1, which closes this cycle. What comes next? Well, you just need to pick anything except for 1, 2, or 3. May I recommend 4? Yes. What happens to 4? 4 and 3, 5, 7 goes nowhere. 4 and 8, 9 still fixed. 4 goes where? 4 goes to 5. Then 5 is fed to the 1, 2, 3, 6 cycle. Does it go anywhere? Nope. So 4 goes to 5. All right, 5. 5 goes to 7. 7 goes nowhere. 7 goes nowhere. 7 goes nowhere. Okay, so 7. Then we go back and we feed 7 in. 7 goes to where? 7 goes to, and see, this is the danger. When you're thinking about 7 goes where, you're tempted to say, 7 goes to 5. No, 7 goes to 3, because that's what this cycle means, right? See, yes, there's right to left thinking, but there's also the loopy thinking. You have to do both. So, okay, 7 goes to 3. 3 goes nowhere. 3 goes nowhere. 3 goes to 6. Now 6. 6 goes nowhere. 6 goes nowhere. 6 goes to 4. And then 4 goes nowhere. But 4 is here. We've closed the cycle. Are there any other numbers that have, 9, right? 8. Okay, fine. Weirdos. I'll do 8 first. All right, so 8 goes nowhere. 8 goes to 9. Actually, here's a thought. If you look at the 4 cycles which are sitting up here, if you look at it, these 2 are what? Disjoint, so they commute, right? And then if you look at, that's it. So that means that this is going to be there. Because you can just commute this out to the side. In fact, we should have done that at the start, right? A smarter way to do this calculation would have been what? To do that to begin with, and to not think about 8, 9. Because it's just fixing everything. Every time we went through 8, 9, and everything I just said, it was always fixing. It never did anything. And there you go. That's the disjoint cycle factorization of sigma tau. What's the order of sigma tau? Least common multiple of what? Actually, was it true for three things? I can't remember. I think it's true for three things. 3, 4, 2. I mean, we can check. Let's see here. What do you got? Because this is a 3 cycle, and that's a 4 cycle, and that's a 2 cycle, and those are their orders. Annoyingly, cycles of odd length are even. Cycles of even length are odd. What can I tell you? It is what it is. It's because the even or oddness doesn't refer to cycle length. It refers to the number of transpositions it takes to make it up, right? But what's this? What's the least common multiple of 3, 4, and 2? 12? Okay. I was thinking 6, but that's wrong. Okay. So, what can I tell you? I'm not a number theorist, all right? I mean, I'm true. So there you go. I mean, if you raise that to the 12th power, what happens when you raise the sigma tau to the 12th power? It raises each one of these to the 12th power, right? Because here's the thing. If we have sigma 1 and sigma 2 equals to sigma 2, sigma 1, then if you take sigma 1, sigma 2 raised to the power n, it's sigma 1 to the n, sigma 2 to the n. That is not always true. If you have non-commutative things, it's not the case that ab to the power n is a to the n, b to the n. Generally, ab to the power n is ab, 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 n-fold times. And you can't move the b and the a around for free because it's not commutative, you know. But here, if it is commutative, so my point is, since this is the disjoint cycle factorization, if you raise this to the 12th power, it raises each one of these to the 12th power. And that to the 12th power is, you know, to the 4th power to the 3rd power. This is to the 3rd to the 4th to the 3rd power to the 4th power to the 4th power to the 3rd power to the 2nd power to the 6th power. In short, your identity to the power in each. Anyway, it's clear that that works. What's the inverse of sigma tau? So because you have disjoint cycle factorization, it's just 1, 2, 3, inverse, 4, 5, 7, 6, inverse, 8, 9, inverse. I'm almost averse to writing this. I think maybe it might be better for you guys if I wrote it this way, because this is what more generally is going to be the case. It doesn't matter here because these are actually going to be equal. And you'll tell me why. This is 3, 2, 1, 6, 7, 5, 4, 9, 8. I mean, that's actually equal to 9, 8, 6, 7, 5, 4, 3, 2, 1. Why are these two equal? Because they're disjoint cycles and they commute, right? That was the point. Disjoint cycles commute. Now, in contrast, if I told you 1, 2, 3, 2, 4, 1, calculate, you know, this is sigma, or let's say it's gamma. What's gamma inverse? Well, I can tell you the gamma inverse is 1, 4, 2, 3, 2, 1. But that's probably not going to be equal to 3, 2, 1, 1, 4, 2. Because those are not disjoint cycles and they don't commute. So we have a more general rule for inverses, which is the socks shoes formula, right? I maybe should have already proved that. I don't know if it slipped through the cracks or not. Do you guys know what I'm talking about, sock shoes? All right. We can derive it. Suppose you have A and B in a group, right? And you're trying to say, I want to see if AB, I want to find the inverse of that. I want to say ABX equals to E. What's X equal to? Right? Because finding X we know that the inverse is unique, so calculate x. That's the unique inverse of AB in the group. So we just have to solve for x. How do we do that? We multiply by A inverse, which simplifies to bx equals to A inverse, right? Because A inverse gives me E, and then EBX is just BX using associativity, definition of inverse, identity. And then multiply by B inverse, what do we get? So the key feature here, guys, is that in a group, you do not commute. So groups don't commute in general. That's the inverse, so I mean, x is, so AB inverse is that. Because that's what x is. X is the inverse of AB if it solves that equation. So, and that's the Stock-Shoes formula. Now, if A and B commute, then we can just say A and AB inverse is A inverse B inverse, or we could say it's B inverse A inverse. It doesn't matter. If A and B commute, A inverse and B inverse commute, right? That sounds like a homework problem. I don't know if it's actually one of your homework problems or not, but it was definitely one I was considering. So it's dangerous for me to solve that, because it could be a future homework problem. I'm not sure. That definitely sounds like a test question, for example. Given that A and B commute, prove that A inverse and B inverse commute. Could you prove that? Any questions about this? Do you need me to do more cycle stuff? Okay. If for some reason later you lose confidence and faith in your cycle calculation, you can come and ask me again about it in office hours. Your secret will be safe with me. It's okay. All right. I know I felt embarrassed to ask after it was taught to me, and then I'm like, all right. I know it's a possible homework question, but let's work it out. Let's try it. Suppose AB equals to BA. Can you prove that? So I'm supposing A and B commute, right, in a group. Can we prove that A inverse B inverse commute? What would you do? Any ideas? Yeah? Let me give it a name. Take star on what? Multiply by blank on the blank. Yeah, I don't think you can go wrong here. B inverse on the left. So if we do that, what do we get? We get B inverse rather, AB equal to B inverse BA, which of course implies that B inverse AB is equal to A. Let me call that star star. Then multiply star star by blank on the blank. You guys fill in the blanks for me. By what? A inverse on the right. Let's see if that helps us out. So then we get B inverse A, B A inverse equals to E. Well, we tried though, right? You tried. Hey, that's how it is. You try stuff. If it doesn't work, you know what? It doesn't work. So what do you do? I do this. Well, it didn't work. Start over.
Multiply by a inverse on the other side. Would that have worked?
Here's what I do. After I try something, whatever comes to mind. If it works, it works. If it doesn't, it doesn't. Then I play a different game. I say, what I want. What do you want? I want A inverse B inverse equals to B inverse A inverse, right? That's my goal. I then try to make reversible steps back to something that's true. So this is true if and only if what? This is not the proof. I'm showing you the scratch work, all right? I'm showing you the man behind the curtain, which may or may not. Oh, how about this? This is, let's see here. A inverse, B inverse, A, B equals to B inverse A inverse AB. Of course, we just proved that this is the identity, right? So that's true if and only if A times, well, maybe if I multiply this by BA, it'll work, right? BA, A inverse B inverse AB equals to BA times E. But of course, this gives us AB equals to BA, which we know is true. There is doubtless an easier proof. It will be added in the YouTube comments either soon or 3 years from now. Who knows? So here's how I'd prove it. I'd say, okay, well, AB equals to BA is true, right? We're given, right? And then what do? You say, well, that implies that, sorry, that implies that B, goodness gracious, what's that? Oh, yes, that implies that BA times BA inverse AB is equal to BA. We can do that because this is just the identity, right? But then that implies that BA, and then by the Sock-Shoes rule, that's A inverse B inverse times AB equals to BA. I'm sure there's an easier way to prove this. And then that implies what? What did I do? I think then I need to, what's that? Multiply what?
Multiply by A inverse and B inverse.
Multiply by A inverse and B inverse?
Yeah.
Okay, so
Or no,
No.
B inverse and A inverse.
which one first?
Yeah.
No, on the left, you don't have A inverse getting E on the right.
Yeah. Yeah.
And that leaves you with the very top line
A inverse, B inverse on the left.
on the left.
Yeah.
A inverse, B inverse, like that? So this simplifies down to the identity. And what happens over here? So this implies then that A inverse B inverse times AB is equal to E, which then implies that A inverse B inverse A is equal to B inverse, which implies that A inverse B inverse is equal to B inverse A inverse. So, yeah. I think this can be simple. I mean, I think that once you see things clearly and we're not talking to each other on a board, and you just sit and meditate on it, you probably can condense it down to about 2 lines if you just choose your steps more judiciously. Yeah. Sorry about that. Oh, here's another one. Could you guys, we today proved that the order of an element is preserved under an isomorphism, right? So another related question is, can you prove that the order of an element is equal to the order of the inverse of that element? Like if the order of G, I'll just keep it finite. If the order of G is equal to n, that implies that the order of G inverse is equal to n. Do you think you could do that? That's another popular test question. Can I erase this before someone points out an obvious 2-line solution? Okay, yes, thanks. There are 2 ways to do this. The one way would be to use that isomorphism theorem we did today, which was that isomorphism preserves the order of elements, right? Oh, but can you... Oh, I guess that's not an isomorphism. I mean, wait, I'm sorry. I was thinking for a second that if we define psi of G equals to G inverse, then that would be an isomorphism. But is that true? Is the inverse map an isomorphism? What if we do like psi of, AB? What's that equal to? AB, ooh, goodness gracious. Not a good sign. AB inverse. And what did we just prove? Oh, yeah. Which is psi of B, psi of A. Oh, no. So apparently, inversion is not an isomorphism. It's an anti-isomorphism. Yeah. So, oh well, my hope of looks like using the corollary using that theorem we had about isomorphism preserving the order of elements of a group directly isn't going to help us out. Unless the group happens to be commutative, in which case we're done. So how would you actually go about proving that the order of G inverse was equal to n? It's almost the same kind of argument we did for the proof today, though. So first of all, you get that G to the n is equal to E, and G to the j is not equal to E for 0 less than j less than n, right? That's what it means for G to have order n. So we want to prove that G inverse has order n. So what should we look at? What's G inverse to the n? This is by laws of exponents, this is also G to the n inverse. But G to the n is E. What's E inverse? So therefore, the order of G inverse is less than or equal to n. So the order of the inverse of G is at most n, given that the order of G is n. And then what do? We need to make sure that no lower power, right? So if we look at G inverse to the j, what's that equal to? That's equal to again, g to the j inverse by laws of exponents. Suppose towards a contradiction that was equal to e. I'm assuming here, 0 less than j less than n, okay? Then suppose towards a contradiction that was equal to the identity, what would that say? That would imply that g to the j is equal to the identity, wouldn't it? Because you can take the inverse of both sides of that equation, right? And that's a contradiction. And you could also prove this for infinite order. The argument would be similar, but I'm tired. You guys have questions, though? We still have a couple minutes. I think I said till 5:15 on my schedule. We don't have to stay till 5:15 if you don't got questions, and it's fine, but yeah. And yes, generally speaking, if you ever need to leave, be in the middle of one of these meetings, you can leave. It's not expected you be here or stay or anything like that. Yep. Yeah, let me put that up so I can look at it. Mission 4? The fiber question. So what's your question about the fiber question?
Just wasn't exactly sure what, especially part A, what it was asking for.
Let me get you started then for part A. So part A, you're supposed to prove that squiggle f is an equivalence relation on the domain of the function, right? I say that this is called the fiber equivalence of the domain of A. So here's the idea. Here's a picture. Here's A. Basically, you can parse A. You can parse A into fibers. All right. So basically, if this is x1 and this is x2, then over here is B. Then this whole fiber maps over to this point. That's f of x1 equals to f of x2, whatever it is. It's an element of B, okay? So everything on one of these fibers maps to a single point over here. I mean, the collection of everything on a fiber maps to a single point. And my claim is that the fibers, which I defined carefully in there, the fiber f inverse of B, it's equal to A in A, such that f of A is equal to B, like that, right? So it's the set of all inputs which share the same output. That's the fiber over the output. That's the kind of big picture, all right? My claim is that these fibers, in fact, partition the domain. Now, I gave a careful definition. I said the 2 points in the domain, x is equivalent to y with respect to f, what? If and only if what? F of x equals to f of y. Now, if you think about that, that really says that that x and y are equivalent if they're in the same fiber. But anyway, this is the definition of an alleged equivalence relation, and so we can check, is it equivalence relation? What do we need to check? Right, so for reflexive, we don't assume x is related to x, right? That's what we have to prove. What can we write down which is true? We could write this, right? Is f of x equal to f of x? Yes, for x and a. Now, the reason that makes sense, you might think I'm saying nothing. I'm actually saying something. There, we're assuming that f is a function. See, if f was not a function, that wouldn't necessarily be true. And that's where we need that f is a function, right there. But because f is a function, it's single valued, so f of x does indeed equal f of x. And so that implies that x is f related to x. therefore, is reflexive. Now, symmetric and transitive, I think, are easier because you say, suppose x is related to y, right? Here, I'll start the next one, too. Suppose x is related to y with f, then f of x is equal to f of y, right? What's that imply? This is kind of stupid, but f of y is equal to, f of y is equal to f of x, which says y is f related to x. There you go. That's symmetry. I'm not going to write down transitivity. I don't want to do the whole problem. It's your homework. I mean, I'm going to write my own solution. I just don't want to write it right now. Part B, I think part B, well, I mean, of course, it's the same as always, right? You assume x is related to y and y is related to z. Your goal is to show that. See here. Hey. I won't come bowling. Is that a threat? I don't know. Listen, part B, if you're stuck on part B, I'm sorry, but that does involve a certain creative leap. I will just tell you this. Those fibers that I'm proposing, right, the equivalence class being the fiber, maybe it's helpful to think about division by 2. If you think about integers, we can partition them into even and odd integers, right? So if you look at that partition, what function takes those as its fiber partition? Like, think about it. What function takes everything that's even and maps it to 0? What function takes everything that's odd and maps it to 1? What is that function? Or we could think about 3. If you think about the integers, you could divide it up into 3z, 3z plus 1, and 3z plus 2. What function takes everything in 3z and maps it to 0? What takes everything in 3z plus 1 and maps it to 1? Everything in 3z plus 2 and maps it to 2. What function is that? That's the function you're looking for. The function that maps everything in the congruence class mod n of A. Well, just to A, I suppose. What is that function? I shouldn't answer this question, but if I say much more, I will tell you this. The function, I believe, is mentioned in the notes. I mean, if you look back at the very start of the discussion of, modular arithmetic, when I first discuss congruence, I don't define it in terms of this sort of thing. I say x is congruent to y if something is true about x and y's relation, right? What did we say to start with? Do you guys already have part B done? So you still have no idea what I'm saying? Not helping. All right, let me give a more solid hint. Think about the remainder function with respect to division by n. Should be able to see that if we think about division by 2, right, then the remainder of division by 2 either maps to 0 or to 1. The fiber of 0 is even integers. The fiber of 1 is odd integers. But this generalizes for other n. We don't have names for those. I mean, the 3 tuples, the 4 tuples, 5 tuples. I mean, I have names for those, but what I don't have a good name for is like the 3z plus 1, or the 3z plus 2.